Hello class, today we are going to go through Unit 6, Lesson number 3. It's going to combine two sections of the textbook, 6.3 and 6.5, which is exploring the graphs of the primary trig functions and the reciprocal trig functions. Okay, so we're going to do each function, its reciprocal on one page each, and basically see the information between the two. What you should notice is that a lot of the characteristics from last unit should be common with these as well. So keep in mind now, instead of labeling the x-axis, or in terms of x we can refer to it as theta, when we label that axis, remember now it has to be in radians, okay, so no more degrees. Alright, so make sure that when you're entering these values in, so when you're entering 0, pi over 4, pi over 2, make sure that you are in radian mode. Okay, so with your calculators, I want you to enter in radian mode, sine 0, okay, and we should get 0. Then do sine pi over 4, okay, and you should get a rounded value of about 0.71. Sine of pi over 2, remember that relates to the numbers up here in degrees, so sine pi over 2 will give us 1. Sine 3 pi over 4 will give us 0.71. Sine pi, that will give us 0. Sine 5 pi over 4, negative 0.71. Sine 3 pi over 2 goes to negative 1. Sine 7 pi over 4, back to negative 0.71, and sine 2 pi should take you back to 0. Alright, so let's graph that right here on the first grid here. So try to do the best you can, make sure you're hitting this max value here, this min value here. And you should remember from last year that the graph should look something like this. Okay, so we start at 0, go up to our max, come back to 0, down to our min, back up to our center value here of 0. Okay, I've just drawn two cycles of sine, so I just did a dotted line here to show the second cycle. And make sure, again, you have it labeled properly. So remember, on this grid here, I have the first grid line is pi over 2. So if you're going to graph pi over 4, you know that pi over 4, I got this side here, so is half of pi over 2. So if you did pi over 2, and then you divided it by 2, that's equal to pi over 2 times 1/2, right? You change to multiplication and flip the bottom fraction, so you get pi over 4. Okay? So we know that pi over 4 is 1/2 of pi over 2. So that's why I did pi over 4 halfway in between the pi over 2 interval. Okay. And with counting, if that's 1 pi over 4, this is 2 pi over 4, which reduces to pi over 2. This would be 3 pi over 4. This here would be 4 pi over 4, which reduces to pi. And this would be 5 pi over 4. Okay, and here would be 6 pi over 4, and then it would keep going, right? This would be 7 pi over 4, 8 pi over 4, which is 2 pi. Okay. All right, now we're going to see what happens when we do cosecant. So remember, cosecant is the reciprocal of sine. So I want you to think of cosecant theta as 1 over sine theta. Okay, so same idea. All right, so if we do, so in your calculator, you're going to write 1 divided by sine and then at those values. So you're going to do 1 divided by sine at 0. Okay, that will give you 1 over 0. Remember, any number divided by 0 is considered undefined. Okay, so that indicates to us that there is a vertical asymptote at theta equals 0. All right, next we're going to do 1 over sine at pi over 4. Okay, so that's 1 over, and you can just get your values from over here, 1 over 0.71, so it's roughly about 1.4. 1 over sine at 1/2, well, that would be 1 over 1, so that would give us 1. 1 over sine at 3 pi over 4 will give us a similar number of 1.4. Again, 1 over sine at pi is the same thing as 1 over 0, so undefined. So we have a vertical asymptote. 1 over sine at 5 pi over 4 will be 1 over negative 0.71, so negative 1.4. And then the pattern continues, and you're going to see that we go to negative 1, negative 1.4, and then again we get another undefined value. So at cosecant of 2 pi, that's the same thing as 1 over sine at 2 pi. Okay, so that gives us something that's undefined with a vertical asymptote. So we can see here a vertical asymptote, there's 3 of them in this one section from 0 to 2 pi. You're also going to notice these other values. Okay. So this shape is going to look much different from this one, but it will be connected in some way. So remember from our last unit, wherever there was a 0 of the original function, so wherever there was an x-intercept, the reciprocal of it should have a vertical asymptote there. So we should have vertical asymptotes at 0, pi, 2 pi, anywhere where it crosses the x-axis, and that's what we do have. So it is going to look like this. Okay. So all these things that I've drawn here, these are the vertical asymptote. So instead of writing x equals, I just wrote theta equals. Same thing. Okay, so these are VAs. And what's interesting about this one, remember the other characteristic that we knew was that wherever an original function had a maximum, we knew that the reciprocal would have a minimum at that same x value. Okay, these two actually share that same point. So at pi over 2 and 1, they both share the common point. On here it's a max, and on here it's a min. So notice it increases to the left and right here. So it gives this kind of parabolic shape. Now keep in mind, wherever the original function has a minimum, we knew from last unit that that meant that the reciprocal has a maximum. So that means we should have a maximum at 3 pi over 2 and at negative pi over 2. And we do. So it goes back and forth, an opening up parabola, a vertical asymptote, an opening down parabola. Vertical asymptote, opening up parabola, and it alternates that way. Notice that from 0 to pi over 2, okay, this little interval here, the graph was increasing here. We know that the intervals of increase and decrease should change for reciprocals. So if it's increasing here, we notice that it's decreasing here from 0 to pi over 2. From pi over 2 to pi, we could see that it was decreasing. And then from pi over 2 to pi here, we can see it's increasing. So all those same characteristics are being met. So now we're going to summarize our findings here. So for the sine function, we know that our maximum and minimum values, our max is at 1 and our min is at negative 1. The period of the sine cycle, so that's how long it takes to complete one cycle. Okay, so that would be from here to here. That's when the shape starts repeating itself. So from 0 to 2 pi, and then after that it repeats. So the period of that is 2 pi. Now the zeros are unlimited, okay? So there's an infinite number of zeros. We notice that the zeros are always at negative 2 pi, negative pi, 0, pi, 2 pi, and forward. So it's at all these integer multiples of pi, right? So it's there. Okay, so we can see I put dot, dot, dot on both sides here, right? Theta equals dot, 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 0, pi, 2 pi, dot, dot, dot. So what we have to do is we have to come up with an equation, because every single time you don't want to write it out this way, or you don't want to list off everything, especially if there's an infinite number. So in math, we try to create an equation that represents all of the possible zeros. So we just said to ourselves that the zeros are always at whole number multiples of pi, right? negative 2, negative 1, 0 pi, 1 pi, 2 pi. So mathematically, we can write that as n pi, where n is an element, and this z value here is integers. Okay, so that's why I have it aside here. Okay, so n is the element of integers, is the z. In your textbooks, though, sometimes your textbook will write it as a capital I. Obviously, that one seems nicer, but in the regular world of mathematics, it's usually the z, so I want you to be able to recognize both. So when we say n is the element of integers, we're saying it's all positive and negative whole numbers. So I could plug negative 10 in there, and negative 10 pi would represent a 0. I could plug in 5 there. 5 pi, yes, that would be a 0. Okay, so it's unlimited, and that's why we can write it with this equation. The domain. The domain of any sine function, it goes on and on forever, so it's theta as the element of real numbers. If you're working with x in your equation, you can say x is the element of real numbers. Our range, we know it goes between 1 and negative 1. So we say y is the element of real numbers such that y is greater than or equal to negative 1, but less than or equal to 1. The equation of the asymptotes, the sine function does not have any, so we should say none. All right, cosecant. So now we're looking at this purple graph here. Okay. Notice that it has no max or min values. And that's because it's composed of parabolas that are opening up without bound and down without bound. Okay, so it doesn't have maximums, okay, absolute max or mins. Okay. So I'm going to put here none for both in terms of absolute. Okay. If I were to ask about local max or mins, yes, it does have that, right? That would be considered a local min, a local min, a local min, a local max, and a local max. Okay, so at the side here, it only has local max and mins. Okay, but no absolute. Okay. All right, now we have to come up with what the period of this is. So how long does it take to complete one cycle? So if you notice here, I'll kind of do this in blue. Let's say one cycle, if we start here, we know that it doesn't come back to this repeating motion until this point here, right? And that's when the upper parabola kind of shows up. So what is this duration? That is 0 to 2 pi. So the period of the reciprocal is also 2 pi. Now the zeros are the x-intercepts. You can see this graph never crosses the x-axis, right? So it has no zeros. Now for our domain. So we can see that our domain is not going to be theta ER because we have breaks at the vertical asymptotes. So we have to generalize that in an equation. So normally we would say theta is the element of real numbers such that theta cannot equal, and then we would list the VAs. Because this one has an infinite number of vertical asymptotes, we have to write it as n times pi. Okay. So we're going to say theta is the element of real numbers such that theta cannot equal n times pi, where n is an element of integers. Okay, so that's just a way of representing the vertical asymptotes. Our range. If you notice, the possible y values are everything from 1 and above, and then everything from -1 and below. So there's two ways we can write this. We can write it as y greater than or equal to 1 and y less than or equal to -1. Okay. Another way that you can actually write this is at the bottom here. Okay, so this here says the exact same thing. It's just not a form we're used to. We're used to having these signs flipped the other way, but if you look at it carefully, it does say the same thing, right? This says y is less than or equal to -1, and it also says y is greater than or equal to 1, so the same thing. I do not care which form you use. And then the equation of the asymptotes are going to be the same equation as the zeros of the original, right? Because the zeros become the VA. So that's why here the equation of the asymptotes are n pi, and that's why they relate to the restrictions on the domain. Okay, so it makes sense here, right? Because the graph does not exist at the vertical asymptote. So really, you never have to memorize this graph as long as you understood the concepts and rules from last unit. Once you draw sine, you're able to actually draw cosecant right off of it. Okay. All right, let's try cos. Okay. All right, so again, make sure you're in radian mode. We're going to do cos of all these angles. So cos 0, you should get 1. Cos pi over 4, we should get 0.71. Cos pi over 2, 0. Cos 3 pi over 4, about -0.71. Cos pi, -1. Cos 5 pi over 4, -0.71. Cos 3 pi over 2, back to 0. Cos 7 pi over 4, 0.71. And cos 2 pi, you should return to 0. Okay, so, and again, this should be familiar to you. Drawing cos should look kind of like that U shape. Okay, so it should look like this. Remember, when you're plotting intervals of pi over 4, I've outlined what grid is pi over 2, so 1 pi over 4 would be halfway in between. Okay, so just a reminder, right here would be 2 pi over 4, right here would be 3 pi over 4, here would be 4 pi over 4, this would be 5 pi over 4. Okay, just reminding you of how to do those intervals there. All right, and like I said, I've done in this little dotted line here, I've just, this dotted curve here is just a second interval of, or a second cycle of cos. All right, so now we're going to do the graph of its reciprocal, which is secant theta. So we can't enter this into a calculator, just like before, so I want you to remember that secant theta is the same thing as 1 over cos theta. Okay, so when we do secant at 0, we're doing 1 over cos at 0. Okay, so that's going to be 1 over, and then we get our answer from over here, 1 over 1, which is 1. Then we're going to do 1 over cos at pi over 4, so 1 over 0.71, which gives us 1.4. 1 over cos at pi over 2, so that is 1 over 0. We know that's undefined, so we have a vertical asymptote. 1 over cos at 3 pi over 4, 1 over -0.71, so -1.4 roughly. 1 over cos at pi, 1 over -1, so that's -1. Should be noticing a lot of the same numbers were the same as with sine's reciprocal as well for cosecant. Okay, here, and that would be, sorry, let me delete this. Okay. Okay, there we go. So, cos 5 pi over 4, we get back to -1.4. Sorry, 1 over that. 1 over cos at 3 pi over 2, we're going to get 1 over 0, again undefined with a vertical asymptote. 1 over cos at 7 pi over 4 brings us back to 1.4. And then 1 over cos at 2 pi is going to be 1 over 1, so we get 1. Okay, so a lot of the same numbers, but you can notice that these y values are happening at different theta values. So let's draw what this one tells us, and notice we've got our two VAs here, so two different locations. All right, so it should look like this. So your VAs should be at negative 3 pi over 2 if you continue the pattern this way. At negative pi over 2, at pi over 2, 3 pi over 2, and 5 pi over 2. Notice these VAs should be wherever there was a 0 in the originals. Okay, so wherever there was an x-intercept up here, there should be a VA down here. Wherever there was a max on cos, there should be a min on the reciprocal. So there was a max at negative 2 pi, 0, and 2 pi. And we have mins there now, as you can see. Okay, so all those same characteristics are held. Okay, so now that we've drawn that in, so again we have opening up and opening down parabolas, we are going to start filling in the charts. So the max and min values for cos, okay, same as sine, max 1, min negative 1. The period for cos, okay, we know is from, right, the U shape finishes from 0 to 2 pi, so period is 2 pi. All right, our zeros. So our zeros for cos is a bit unique here. So our zeros for cos are at negative 3 pi over 2, negative pi over 2, pi over 2. So most students will immediately think that we can say that it's at pi over 2 times n. So just like with sine when we did n times pi, they think that when we're doing this, that you can write it like this. So look at this bottom right corner. So students think we could do pi over 2 times n. The problem with this is that while it works for one, and some of the other ones, what if we were to plug in 2? Okay, so if I were to plug in 2, I would get pi over 2 times 2. 2's would cancel out and I'd be left with pi. Pi is not a 0. So my formula is incorrect, just like I wrote here. If I let n equal 0, okay, I would get theta equals 0. If I go to the graph, 0 is not an x-intercept. So this is not good, okay? Even though I understand that might be your first instinct. So we have to ask ourselves, how do we come up with an expression for this? Okay, so what I do notice is that the zeros happen at, yes, it is a multiple of pi over 2, but it's at all odd integers of pi over 2. So the zeros happen, okay, so zeros here are at negative odd integers. Okay, so it's that odd part. Okay, multiplied by pi over 2. Okay. So we have to think to ourselves, how are we going to write that out in a mathematical formula? Okay, so we can bring this down. Okay, we're thinking to ourselves here. All right, so in math, I want you to think. In math, we know that we can represent even numbers by saying 2 times n, because 2 times any number gives you an even number. So if 2n represents an even number, then that means we can represent an odd number by doing 2n minus 1, right? If you have an even number and subtract 1, it's odd. Okay, so you can do 2n minus 1 or you can do 2n plus 1. Either way, it represents odd numbers. So if I want to say that cos has zeros at odd integer multiples of pi over 2, I can write it like this. Okay. Let me put it here at the bottom, like here in purple. So I'm going to say theta equals 2n minus 1, which is odd integers, okay, times pi over 2, and n is an element of integers. So that tells any person that I can plug any integer of n into this formula, and it will create for me all the possible zeros. Okay. So this purple way here is the same way as listing them, right? I can do dot, 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 negative pi over 2, 3 pi over 2, dot, dot, dot. Okay. So these are the formulas I want you to get used to down here. Okay, so this one does not work. All right, the domain is theta as an element of real numbers. The range is the same as sine. Y is greater than or equal to -1, less than or equal to 1. And we know that cos has no asymptotes. So now we're going to look at secant. Okay, so secant does not have any absolute max or mins. Okay, so I'm just going to write here absolute. Okay, at the side here I'm going to write that it does have local max and mins though. Okay. All right, so up here would be the local mins, up here would be the local maxes. Okay. The period for this. So I want you to outline where you see a cycle repeating itself. So for example, here in purple, I have outlined where I see one cycle. Okay, so from here to here, right? An opening up and an opening down, and then it starts to repeat. So if I wanted to find the length of this, I'm going to do the end x value minus the start x value, or the theta value. So I'm going to do 3 pi over 2 minus negative pi over 2. Two negatives make a positive, so I get 4 pi over 2, which is 2 pi. Okay, so this secant also has a period of 2 pi. The zeros of secant, we can see it never crosses the x-axis, so none. The domain, so this exists for all real numbers such that, and then we have to put the restrictions for the vertical asymptotes. So an expression we're going to use to represent the vertical asymptotes is going to be the expression we use to represent the zeros of cos. So this purple equation down here. So we're going to say theta is an element of real numbers such that it cannot equal 2n minus 1 times pi over 3, where n is an element of integers. So this came right from here. The range is going to be the same as cosecant, so y can be less than or equal to -1 or greater than or equal to 1. And lastly, our equation for our asymptotes is going to be the same as the equation we used in our restriction, so 2n minus 1 times pi over 2. All right, and now we have one more to tackle, and that is tan. So to do tan, again, you can just enter into your calculator there. So you can do tan at 0, okay, and you should get 0. Another way to think of tan, if you'd like, is to think of tan as sine over cos. Okay. So if you're doing, let me fix that there. So if you're doing tan at 0, that's really sine 0 divided by cos 0, okay? Because tan is always sine theta divided by cos theta. So if you do that, sine 0 is 0, cos 0 is 1, 0 divided by 1 is 0. Okay, so that's how you get 0. Tan pi over 4, you should get 1. Tan pi over 2, same thing as sine pi over 2, which is 1, divided by cos pi over 2, which is 0. That is, any number divided by 0 is undefined. Okay. So we have a vertical asymptote in tan. So tan is the first primary trig ratio whose graph has a vertical asymptote. And it all comes back to the fact that tan is sine over cos, and therefore wherever cos is 0 is where something's going to be undefined. We can fill in the rest of our chart. Again, you can use the method I'm using up here in green, or you can use your calculator button for this as well. And we should see here we go from 0, 1, undefined, to -1 at 3 pi over 4, 0 at pi, 1 at 5 pi over 4, undefined at 3 pi over 2, -1, and then 0 at 2 pi. Okay, so let's take a look at what this one's going to be a little different. Okay. And this is our graph. So it kind of has, what it should look like is kind of those cubic S shapes a little bit. And it should look like they're going up to the right. Okay, so curving more to the right. So from below up to the right. So make sure that you have in clearly the equations of your vertical asymptotes. Okay, so they occur at negative pi over 2, pi over 2, and 3 pi over 2. And then those S shapes should be occurring. And notice that they should go through at 0, pi, and 2 pi. Okay, so obviously for this one, we would have to test more values to see how this shape was happening. Okay. So the blue graph is tan. So again, what I want you to recognize is that tan relates to sine and cos. So because tan is sine theta over cos theta, what are the rules from last unit? We know the zeros of tan should be where the numerator equals 0. So that means it should be where sine theta equals 0. And that's true. Sine theta equals 0 at 0, pi, and 2 pi. And then obviously it continues. We know from last unit that wherever the denominator equals 0 is where there should be a VA. So because cos theta is in the bottom, we should have a vertical asymptote wherever cos theta equals 0. Cos theta equals 0, negative pi over 2, pi over 2, 3 pi over 2, and forward. All right, now let's do cotangent. So cotangent, we have to keep in mind, is the reciprocal of tan. So it's 1 over tan theta. So for this one here, you can do 1 over and then whatever answer you got in this table over here on the left. Or you can think of 1 over tan theta as the reciprocal of sine over cos. So cos theta over sine theta. Okay, so you can think of it either way. Basically, you're going to take all these answers here and you're going to take their reciprocals. So cotangent of 0 is 1 over tan 0. Okay. That's going to give you 1 over 0, so undefined vertical asymptote. Cotangent of pi over 4. That should be cos pi over 4 divided by sine pi over 4. We should get an answer here, or you can take the answer from up here, of course. Okay, and do 1 over 1 and get 1. Cotangent of pi over 2. So I'm going to go to pi over 2 here. It used to be 1 over 0. So that means its reciprocal is going to be 0 over 1, which is going to be 0. Okay, so 0 over 1 is okay. You're going to do this for the rest of the values. Okay, so take the reciprocal of the one at 3 pi over 4, so that'd be 1 over -1, still -1. This one was 0, so 1 over 0 is the reciprocal, so you get undefined. You get 1, 0, -1, and undefined again at the 2 pi mark. So cotangent will have vertical asymptotes as well, and we're going to see what its shape will look like too. So its shape will look similar, but a few changes. So it's going to be here in purple. So it has that same cubic S-shape look, but notice now these arms look like the reflected versions of the blue ones. So tan has the increasing S shapes, okay, and cotangent has the decreasing S shapes, okay. They have different x-intercepts, okay, and this has different vertical asymptotes, right? So remember, cotangent is cos over sine. So in cotangent, you should have zeros wherever the numerator equals 0, and that's true. We had at negative pi over 2, 3 pi, 3 pi over 2. And cotangent, since sine theta is in the denominator, that wherever sine equals 0 is where you should have a VA. And that did switch. Now we have a VA at 0, pi, and 2 pi. Okay. So just keep in mind, cotangent has the increasing S-shaped look, cotangent has the decreasing S-shaped look. All right, so for tan theta, looking at the graph here, you can see there are no max or mins, no local or absolute. Okay, so none. Now let's find the period of tan. So if you look from here to here, okay, so this is one cycle. Okay, just one of those S shapes is one cycle because it immediately repeats the next time. So one period is going to be whatever the distance is from pi over 2 to 3 pi over 2. So if we do 3 pi over 2 minus pi over 2, that is a length of pi over 2. Okay. My apologies, pi. All right, let me write that out. So that would give us pi. Okay, so let me write it in blue, sorry. The period is going to be equal to, so we do 3 pi over 2 minus pi over 2, okay, and that will lead us to 2 pi over 2, and that reduces to pi. So this is something else that's unique. The period for tan is pi, not 2 pi like the other two functions. Okay. So the period here is pi. How do we come up with an equation for the zeros? So the equation for the zeros are going to be 0 pi, 2 pi. So it's going to be all integer multiples of pi. So we know how to do that from the sine function. So the zeros are at n pi, where n is an element of integers. The domain is all values except for the VAs. Okay? And remember, the VAs occur where cos theta equals 0. So we know how to represent that. Right? We represent that by saying theta cannot equal 2n minus 1 times pi over 2. N is an element of integers. So that is basically saying at all odd integer multiples of pi over 2. Okay. So that should match with the equation of our asymptotes here. Okay. What's also new here is that the range of tan is all real numbers. Because see how it extends like the cubic shape, so it reaches all y values. So our range is YER. All right, and now cotangent. So looking at the purple graph here, it also has no max and mins. The period for this one, so if I were to outline here, so this would be one cycle. So the period from here to here, okay, we can see from 0 to pi, we can easily see that is just pi. So it too has a period of pi. The equation of its zeros are going to be different. So its zeros occur at the odd integer multiples of pi over 2. So we know to represent that as 2n minus 1 times pi over 2. The domain, so it has to have the restrictions of the vertical asymptotes, which are at integer multiples of pi. So theta cannot equal n times pi. And the range for this one is also YER, as we can see. And then the equation of its asymptotes are at n times pi. Again, I'm going to just write at the bottom here. So the equation of the asymptotes here are the zeros of cos. Okay. And the equation of the asymptotes here are the zeros of sine. Okay. So let's summarize kind of what we've noticed here on the next page. I'm just going to go down to the key ideas here. Okay, we'll come back up to this in a second. So we should notice that the graph of the reciprocal trig function is related to its corresponding primary function. Okay, so the vertical asymptote corresponds with the 0 of the primary trig function. Okay, so same idea. The VA of the reciprocal, okay, comes from the 0 of the primary trig function. Okay. You should notice that the reciprocal function had all the same positive and negative intervals. Right? So if we go back up, it was above the x-axis, okay, from here to here. Okay. So from 0 to, for example, from 0 to pi over 2, it was above the x-axis. And if you go to 0 to pi over 2 for the reciprocal, it too was above the x-axis here. From negative pi over 2 to 0, it was below the x-axis. From negative pi over 2 to 0, the reciprocal was also below the x-axis. Okay, so that stayed true. The intervals of increase and decrease switch, we knew that. Okay, we saw that in our example, so those should swap. Okay. The range of the primary trig functions include 1 and negative 1. So a reciprocal function intersects its corresponding primary function at the points where y equals 1 and negative 1. So that's why we have POIs there. Okay, so same as last unit. And also the same as last unit, if the primary trig function has a minimum, okay, then on its reciprocal, it's going to have a max at the same theta value, local max. Okay, and if the trig function has a local max, then its reciprocal will have a local min at the same x value. Okay, and we saw that. So what I want to highlight here was that everything is the same as Unit 5. Okay, all same Unit 5 material. All right, and then the last few bits that I want you to kind of refresh your memory with here that we're going to get into a bit more. Just remember key terms like amplitude, which is half the distance between the max and min values of the range of a function. Okay, so let's just remember that amplitude is the absolute value of A, and that can be found by doing max minus min divided by 2. Okay. If I refer to the axis of the curve, that's the horizontal line that cuts the function in half. Okay, so how do we find that given some key values? So that's a horizontal line, so it's always y equals, and then you do max plus min divide by 2, right, to find the halfway point. And lastly, we kind of worked on this already in the lesson, the period of the function should be the horizontal length of one complete cycle. Okay, so you care about how far you've traveled on the x or the theta axis. So that should always be, you know, the theta value of the end of the cycle minus the theta value of the start of the cycle. And then later on when we get into transformative equations, we should remember from last year that the period was always 360 divided by k, and now we're working with radians, so it's always going to be 2 pi divided by k. Okay, so we'll get into more of this later, but just a little refresher of some of the key terms. All right, I hope you enjoyed learning about the graphs of the primary trig ratios and radians, and hopefully you enjoyed also seeing what their reciprocal functions looked like as well. Okay, good luck with the homework, and we will see you for the next lesson.